demonstration helps illustrate how these factors interact. The equipment allows the comparison of various nozzle choices, spray pressures, spray volumes, and angles of application. A fan will simulate the effect of wind. Let's start with an extended range flat fan nozzle, perhaps the most commonly used nozzle in agriculture today. Though not designed specifically to control drift, the extended range flat fan can adequately reduce small droplet volume when the accompanying variables of spray pressure and spray volume are adjusted. Another application misconception suggests that high pressure is necessary for effective penetration of the product into the target zone. But using this small orifice extended range flat fan nozzle in a simulated 5-mile-per-hour wind, we can see, by increasing spray pressure to 40 psi and above, the creation of an abundance of micro-sized droplets, an obvious increase in drift that actually reduces coverage. Now, by lowering spray pressure back to the 20 psi range, we can create larger droplets, in turn reducing the potential for drift. Still, for proper coverage at lower spray pressures, applicators must work with higher spray volumes. This can be achieved through a combination of reduced sprayer speed and utilization of nozzles with greater orifice size, allowing larger flow rates per minute, while dramatically reducing the percentage of ultra-fine spray droplets. For example, under identical 5-mile-per-hour wind conditions, watch the performance of this large orifice extended range flat fan nozzle under varying spray pressures. Now, comparing the large orifice extended range flat fan side by side with its small orifice counterpart, we can see a significant difference in physical drift. Spray pattern shape can also affect drift potential. Here, we compare an extended range flat fan 80-degree nozzle with a 110-degree extended range nozzle. While spray drift appears to be negligible for either nozzle application at 20 psi spray pressure, once we increase the pressure to 50 psi and add a 5-mile-per-hour wind, the advantages of the 80-degree nozzle are evident. Aside from the wide variety of traditional extended range flat fan and flood spray nozzles, there is a new generation of nozzles designed specifically to reduce drift. For example, let's look at the turbo flood jet nozzle, seen here at 20 psi pressure and a 5-mile-per-hour wind. With its pre-orifice turbulation chamber design, this new nozzle produces larger, more consistent droplets in a uniform pattern by directing the spray downward instead of on an angle, usually 45 degrees to the rear. Comparing the turbo flood jet side by side with a conventional flood nozzle, note the significant improvement in drift resistance. Here's a flat fan extended range 110 nozzle, demonstrated at 30 psi with a 5-mile-per-hour wind. Compare this nozzle with another new design, the turbo flat fan, under identical conditions. And now, side by side. As you can see, the turbo nozzle design is obviously a better drift performer, especially under windier conditions. When an applicator is subject to operating at a variety of sprayer speeds, he needs a nozzle design that is less sensitive to pressure variance. The Turbo Drop Venturi air-inducted nozzle allows reduced drift performance at higher spray pressures. Here, we see this new nozzle spraying at 40 psi pressure in a 5-mile-per-hour wind. This extended range flat fan 8003 nozzle has the potential to produce a large volume of spray droplets under 200 microns in size. At 40 psi spray pressure, however, this nozzle is obviously more prone to drift than the Turbo Drop Venturi air-inducted design. Additionally, the performance of more conventional nozzles can sometimes be dramatically improved by merely adjusting the angle of orientation. Here we see a raindrop hollow cone nozzle, which features a secondary swirl chamber at its tip that reduces pressure and creates larger droplets. However, this design is more susceptible to side wind drift, moving the spray pattern off the end of the boom, because it must be operated at a 30 to 45 degree angle to achieve pattern uniformity. But now, improved technology, including the Turbo Flood, Turbo Flat Fan, and the Turbo Drop Venturi air-inducted nozzles, allows spraying straight down at the target, allowing less chance for wind interference. No matter what type nozzle you choose for your application, and no matter how diligently you monitor spray pressure and volume, if the nozzle becomes worn or damaged, it will invariably produce an irregular spray pattern, greatly increasing the number of small spray droplets and leading to potential drift problems. As a result, nozzles should be thoroughly checked prior to every application. And remember, using nozzles with larger orifices and lowering spray pressure, practices that automatically reduce drift, will also reduce nozzle wear and tear, further reducing drift potential. Finally, the simplest and cheapest equipment factor in drift management also may be the most important: spray boom height. The correct height for any system is determined by nozzle type, spacing, and spray pattern angle. Obviously, the closer the nozzles are to the target, the less chance there is for off-target movement. Depending upon all the variables, a boom height of 18 to 20 inches above the target is recommended to best reduce drift when using crop protection products designed for foliar application.